Okay, so 6.1, estimating with finite sums. This is kind of an introduction to what we're going to be doing coming up, conceptually speaking, kind of what we're going to be trying to do. So suppose we have a car traveling at 65 miles an hour for 2 hours. So let's see, 65 miles an hour buzzing along for 2-hour time period. Okay, what is the accumulation of miles for the sum of instantaneous rates over the 2 period? In other words, how far did they actually drive? If they drove 65 miles an hour for 2 hours, how far did they travel? 130. How'd you get 130?
2 times 65.
Yeah, 65 times 2, or 65 times 2, which is what? The area of that rectangle is. Okay. So if we take a rate over a period of time, we can get the distance traveled. This is kind of an introduction to what we're doing. The area underneath our curve over a particular time period gives us our distance traveled. Okay? If we're not going a nice steady rate, it's still the same concept. Okay. So in addition to the method described to describe functions that are changing and give an instant differentiable calculus, we need a method to describe how those instantaneous changes could accumulate over an interval to produce the function, integral calculus. So what we've done, what we're going to do is it's going from the derivative gives us our rate of change, particularly our instantaneous rate of change. What we're going to do is we're going to take that rate of change and go backwards as it came out. We're going to be going backwards is essentially what integration does. We're going to find the accumulated amount rather than how fast things are changing. We're going to say how much did they change. Not how fast, but how much. Kind of going in the reverse of what we did. That's the idea of integration. And basically, the next 2 chapters are techniques to do that. Yeah, go ahead. Mm-hmm. Okay. Suppose a particle starts at x equals 0 as it moves along the x-axis with velocity of v of t equals 3t plus 2 for t equals greater than 0. Where is the particle x of t after 2 seconds? So it begins at 0 and moves with a particular velocity. Now, when it was a constant steady velocity, what did we do to figure out how far it moved? We took how far it traveled times the speed that it traveled. Well, our speed is not a constant. Our speed changes as time changes. The previous one, that's the previous, there we go. Previous one is traveling at 65 miles an hour constantly. We don't have it speeding up and slowing down, nice straight, going through the middle of Nevada. You know, actually not Nevada because you can go a whole lot faster than that, but you get the idea. Going 65 miles an hour, it's at the cruise control, you're just moving right along. Okay, no speed change during that 2 time-hour period. But if we look at this one, speed does change. The velocity changes as time progresses. At time 0, it's going one speed. At time 2, it's going a whole different speed. But we can still do the same thing. Okay, we can still find the same thing because we're going from 0 to 2. And what we can do is still find the area underneath the curve. That's all this is. Same concept. Even though the velocity is not a constant velocity, all we have to do is figure out what that area is there. Well, what kind of shape is this?
Triangle.
No, it's not a triangle. It's a trapezoid. Turn your head sideways. If you can't see it, turn your head sideways. It's a trapezoid. You better get used to that one. We're going to do a lot of trapezoid work in here. So the area is 1/2 base times height 1 plus height 2. What it in this trapezoid, what is the length of my base?
8.
Or I should say the length of my height, base 1 and base 2. My height is this distance here. So it's 1/2 times 2 times this length plus that length. 2 plus 8. Which gives me 10. It's now at 10. It started at 0, it's now at 10. Did not move at a constant speed to get there. It started out slow and got faster and faster. This time went on.
So all we need to do is figure out the area.
Right.
Okay.
Questions so far? Yes.
Why is it 2 plus 8?
Because it's base 1 plus base 2, right? Area of a trapezoid, and you really need to have this formula you're going to use this a lot over the next couple of months, and particularly the next few days. But the trapezoids are huge, and the trapezoid rule is something we're going to come up with. You're going to use trapezoids an awful lot. You're going to have to use, usually anymore, AP is asking questions where you have to use trapezoids as part of finding your answer. It's one of the things you're going to have to do. You need to have that. And the reason I did this is my height here, because the height is the distance between the two parallel sides, and the two parallel sides are base 1 and base 2. And that's the formula for the trapezoid. You better remember that formula. Learn it. Know it. Live it. Questions? So yeah, basically it's find the area under the curve. Curve. Okay. So if it's not a straight line, this makes things a little more difficult. What if u(t) is not a constant like hard going 65 under cruise control? Suppose f of x equals 16 minus x squared on the interval from 0 to 4. I still want to find the area under the curve. But literally, I have a curve. It's not straight. It changes. It's not even close to straight. So what are we going to do now? We're going to estimate. Okay? With n as the number of subintervals, we're going to use 4 on these problems here. We don't want to use much more than that when you're doing it by hand. I think 6 is about the most you really want to do by hand. Trust me. Although we're going to have one coming up that you're really going to hate. This is going to be huge. Okay. We can do a caveman calculation. I love this. Instantaneous rates 3 ways: LRAM, MRAM, and RRAM. RAM stands for rectangular approximation method. Notice the third word in RAM is approximation. Okay, or sorry, the second word I meant the second word, approximation. You were right, I was wrong. Okay, this is an approximation. This is not exact. We will come up with methods to do this in exact later, but this is for approximation. And RAM is rectangular approximation method, which means we're going to break them up into rectangles. The difference between LRAM, MRAM, and RRAM are where do we get our height of a rectangle? So what we have is we have a subdivision. We're going to divide this into 4 even parts. There's 1, there's 2, there's 3, there's 4. 4 even parts. So the width of our rectangle, or one of the dimensions of our rectangle, is this. And then the other one, our height, comes from whether it's LRAM or RRAM or MRAM. But these are the 2 sides of my rectangle. With LRAM, we're going to use the left-hand side. So we go our rectangle, we go until we hit the left hand, our curve hits what's on the left-hand side, and that's the top of our rectangle. So for LRAM, that's our first rectangle has that height. Our second rectangle Looks like that, the left-hand side. The left-hand side determines the height of a rectangle. On each one of those. That's an LRAM. I go up the two sides, and I go until my left hand stops, hits the curve, and then I go over, that's the top. My right hand just goes up as high as my left hand does. When my left hand hits the top of the curve, that's when I go over, that's where I stop. Okay. So I'm going to add up those 4 rectangles. Find the areas and add them up. This will give me an approximate area underneath the curve. Okay, well, the width isn't too bad because I go from 0 to 4, right? This is 4 here. So what's the width on each one of these? 1. That's nice. Makes it really easy. Then I got to figure out what my heights are. Well, that one's not too bad. It's 16. So 16 times 1 plus, how tall is my second rectangle? It's 15. And if you don't have a graph to get it from, where can I get to 15 from? Well, what's our equation? We put in what our x coordinate is. It's 1. 16 minus 1 squared is what? 15. So 15 times 1 plus, what's the height on the third rectangle? 12. 12 plus 1, or sorry, 12 times 1. Plus, and what's our last one? The height is 7. 7 times 1. Okay, 16 plus 15, that's 31. 31 plus 12 is 43. 43 plus 7. So our LRAM is 50. Is this an over approximation or an under approximation? Over. Are left-hand approximations always going to be over? No. Sometimes they will be under. It depends upon whether your original function is increasing or decreasing. If your original function is decreasing, a left-hand, an LRAM will be an over approximation. If your original function is increasing, it will be an under approximation. It all depends upon what the original function is doing. Sometimes it'll be over, sometimes it'll be under. Okay. What would make it more accurate? What's the one thing that would make it more accurate? Having more rectangles. If I have more rectangles, if I went halfway up and over, and then halfway here and then over, if I divide them all in half, if I doubled the number of rectangles, the amount that's over would be less. It'd be more accurate. If I doubled that, it'd be more. If I doubled that, it would be more, right? The more rectangles, the more accurate, because the less I would have over. Each one would still be a little over, but it wouldn't be as much. We're going to add an infinite number of them together at some point. Not today. Not today. Today we're going to do the same thing with RRAM. So same idea, same problem, except for it's a right rectangle, which means that we go up until the right-hand side hits. So I go up, and there's the height of my first rectangle. And if I go up on the right-hand side, there's the height of my second one. There's the height of my third. What's the height of my last rectangle? 0. It goes across. Is this an over approximation or under approximation? This would be an under approximation. Calculate it out. Okay. So what's the height of our first rectangle? 15. So I have 15 times 1. Height of the second rectangle is 12 times 1. Third rectangle is 7 times 1. And the last one is 0 times 1. So 15 plus 12 is 27. right? Yeah, plus 7 is 34. Big difference between the two, isn't it?
Oh, yeah.
Between 50 and 34. Okay. Big difference between the two. Yes.
Aren't they like equally different, like wrong in the decimal way, like the standard error?
Well,
No.
you know, we can figure it out exact at some other time, and we can kind of do that. It's hard to say because it depends upon the curvature. It's not just increasing or decreasing, but the curvature has an effect on what's out. It would be pretty close. If you were to take the average, boy, you'd be really close to what it was. And I can figure out exactly what it's supposed to be pretty quick. But that's another time for you guys. It's a whole other time to get the exact. I mean, that's we got to do a lot of stuff before we get to that point. But it would be pretty close to halfway. So the next one would be MRAM, which means your height is where? In the middle. So our first rectangle goes up, and our height is halfway in between. It's the middle one. It's not the right or the left. It's where it's halfway in between. It's the middle. It's actually technically, I want to find behind my rectangle. I go up the middle until it hits, and then I go, okay, that's the top of my rectangle. I go up the middle of this interval until it hits. And that gives me my height of my rectangle there. I go up the middle until it hits. And that gives me that one. Now, here's the problem. They're not exactly on any of those lines. You actually have to calculate where the middle is. Remember our function? F of x, 16 minus x squared. So what you have to do to find the midpoint of every interval, you have to take, or to find the height, you have to take the midpoint of every integral and plug it into the function to find that height. So you need to find f of 0.5. You need to find f of 1.5, f of 2.5, and f of 3.5. Those are your midpoints of your intervals. If you don't have a grid, you can still find the right and the left and the midpoint by plugging in the x values into your function. That will give you the height of your rectangle. So that's what the height is. The height is the function at that point. It's the y value. It's the f of x value. Please calculate MRAM. Okay, so if we're doing MRAM, we have to find the height of the midpoint. Now, the nice thing is, all our widths are 1, so you just multiply all those numbers times 1 individually and then add them together. And what do you get? 43. So I got 43. The exact value using methods you will learn. 2 and 2/3. 42 and 2/3. Wow. And this is a fairly straightforward curve. I mean, you could have something that goes from A to B that does something like that. And you got to find the area there. We will learn how to do that.
Now, why would we want to know?
You'll see as we come along. We'll actually get to applications at the end of after doing all the integrals, but there are a few applications beforehand. And really, there's some good applications. There are some really good ones that'll work. But the idea is, let's say I know my velocity. If I know my velocity, I can find my position. We have an equation. So what we've been doing so far in here is if we have an equation that describes where something is, and we can deduce that equation from observations, come up with something. This is what they really do. Is they will make observations, collect data, and you can come up with an equation from that data. And we have something from where something is. We can use derivatives to figure out how fast it's moving. And we can use the derivative of that to find out its acceleration. Now we will be able to go the other direction. If I know something's acceleration, I can come up with a velocity equation for it. If I can come up with a velocity equation, I can come up with a position equation for that same thing. So if we can figure out how fast something is falling, let's say, we can work our way backwards. Yeah, we can actually work our way backwards.
Is that what the antiderivative is?
That's kind of, it is and it isn't, but that's what it's easily used for. There are other methods, and antiderivatives will just be the easiest method. Trust me, it will be the easiest one. The only one that's easier is plugging in on your calculator. We'll work on that. But you will have to be able to do it by hand as well. Okay. Suppose a motorcycle is accelerating from 0 to 142 miles per hour in 36 seconds. Use the data table with the velocity recorded at certain instants to find out how far the motorcycle travels in 36 seconds. Average LRAM and MRAM. This is a very common problem. You will have homework problems like this. Often it's easier to collect the data from where something is. Okay, where is it now? Where is it now? Where is it now? Where is it now? And use that data to figure out distances. Or you have a speed track. You can look at the speedometer on your car and notice, hey, after 1 second, I'm going this fast. After 2 seconds, I'm going this fast. After 3 seconds, I'm going that fast. You can use that to deduce. That's kind of what we're doing here. Yes, it is a much larger table. Okay. But we can figure this out. It's actually not as bad as it looks. Here's what you have to do. Turn your head sideways. Look at it from this direction. These are our widths of our rectangle. Our first rectangle is 0.001 units wide, because that's 36 seconds. When you break it down, this is how much time you have of an hour. This is the width of our rectangles, which means that these lengths are our heights. So for our first rectangle, if I'm doing LRAM, if I move across here with my left and right hand on one side of the rectangle, one on the other side of the rectangle, if I do LRAM, what is the height of my first rectangle? 0. So for LRAM, my first rectangle is 0.001 times 0. Because as I move down there, that's the height of my first rectangle. So if I go to the next rectangle, and if I move along here with my two sides, my left and right hand, what is the height for an LRAM of the second rectangle? 40. So my next one is, and how wide is it? Is 0.001 units wide times 40. Okay, do you guys get the idea what's going on? And when you're doing the RRAM, what are you going to use? What's the height of my first rectangle with RRAM? 40. And the next one, it would be 62. So here's what I want you to do using this table of values. Use average the RRAM and the RRAM and LRAM to estimate the total distance traveled. Time times velocity gives you distance. right? Dirt. Distance equals rate times time. I'm going to use a lot of dirt in here.
Getting it from the rightmost value of the triangle is going to be a higher number than the I just can't imagine how you make it because you're not flashing. I don't know. Get the same thing with the heights.
So right.
Okay, so if you stop and think about it, and I've only plotted a few points. Okay, if you take a look at it, graphically speaking, if you were to plot these points out, these are x coordinates, those are y coordinates, you would get a curve. What are you doing with the LRAM? You're going with your left-hand height. Something like that. What are you doing with your RAM? Right hand. And so on. Where do these values come from? Well, our left-hand one goes from 0 to 0.1. This is the width of our first rectangle, 0 to 0.001. That's the x-coordinates. It is height of 0 on the left and a height of 40 on the right. That's where you're getting it from. So if you look at this, like I said, if you kind of turn your head, this is the x-coordinates. These are the corresponding y-coordinates that go with it. Make it work it out. So when you do your LRAM, your first one has a height of 0, and our last one has a height of 137. When you multiply them and add them all together for your LRAM, you get 0.898. Because you get 898 when you have all together besides 0.001, move the decimal 2 places. So you've got 8.98 miles. Okay.
Why is the last one not the last thing?
Why is the last one not? Because when I do my last rectangle, this is the width of my last rectangle. Sorry about that. My last rectangle is that wide. I'm going up the left-hand side to find my left-hand height. That's my left-hand height. Okay. So on my first rectangle, when I'm doing my RAM, .001 times my first height. When I'm doing RAM, I go up the right-hand side of my rectangle. So that would be 40. And my last one, because it's the same width, I go up the left-hand side. My last one is a height of 142. And when you do your RAM, you get 1.040 miles. And what's your average? What'd you get? Come on, I know somebody had to have done it. 0.969. Yeah. Which one's more accurate? Which one's closer? And obviously, the average is going to be the best one that you have. Kind of depends upon how this curves. Because it is increasing, then my left-hand one will be an underestimate, my right-hand one will be an overestimate. But how much over or under depends upon the concavity. The more concave something is, whether it's concave up or concave down, also affects your estimate. And those are questions that are going to come up at a later time. Which one's going to be more accurate along those lines? And there are other methods too. There's the trapezoid method, where instead of finding a rectangle, you take the two endpoints and you draw a line across and you do a trapezoid using the two of them. That would be even more accurate than a rectangle. But that is still only an estimate. it is still only an estimate. And whether that's an overestimate or an underestimate, that truly depends upon the concavity of the function. If it's concave up, trapezoid will be an overestimate. Concave down, trapezoid will be an underestimate. Foreshadowing. What you're doing today is going to be doing things like this and like the previous ones. Some will be nice straight lines, just figure out the area because it's nice straight lines. Other ones, you'll have to break it down into parts and estimate using LRAM and RRAM. Do not forget this lesson as we move on through the next couple of chapters. I have had students, almost every year that I've taught this, that will get to a problem near the end. And they go, I can't do this problem. What we just learned doesn't work. Yeah, but what we did 2 months ago will work just fine. So there may be times when doing it by hand, if you don't have an equation, but I give you data, you have to go back to something like this if I give you data. If I give you an equation, there's different methods of doing it. If you don't actually have the equation, you have data, this is the kind of stuff you have to do with data. And the other methods we're going to learn later on will not be as effective as this will be. Okay, so you kind of have to, don't forget, it's a real common thing versus, Mr. Orsi, you didn't give us an equation, what am I supposed to do? Yeah, you can still figure it out. You just have to remember what we did a couple of months ago. Okay, so don't forget this lesson. Don't forget area under the curve and how to do that kind of stuff. Okay, questions? Nice simple beginning to what we're going to begin, what is going to be really difficult later.